There it is. Hi, we're going to walk through some stuff with this and show you how to solve a basic series parallel circuit. We did this in class today. So here's what we're going to do. We're going to solve and we're going to break it down into loops at a time. So we're not going to have to do the whole thing. We're going to take this chunk from here to here, and then we're going to take this piece, then this piece, then this, then this, then these last two. Basically, that way we can break it out and see what exactly we're doing. So first off, we're going to solve the first parallel loop, and I'm just going to write out my notes so you can see what I'm doing. So my first parallel loop goes like this. I've got resistor number 1, which is a 1200 ohm resistor, 1.2K. My resistor number 2 is a 1700 ohm resistor. Okay, so if you look right here at this page, you can see the numbers right there. So I'm going to put those in. Now I'm going to break out my calculator here in a minute just because I'm not going to try to do this in my head and screw it all up. So I've got, to get this total resistance of this loop, I've got R1 to the -1 plus R2 to the -1, and then we'll have to invert that back out to get our resistance for that loop, which we'll call RL1. Now, if I plug those numbers in, I've got 1200 to the -1 plus 1700 to the -1, and then I'll have to pull those out, like I said, to get that RL1. So plugging that into my calculator, I'll type it in just exactly how I state it. So I go parenthesis 1200 to the -1 plus 1700 to the -1. Close that parenthesis, invert that back, and push that button again. So I've got 703.4482. I'm just going to stop at the 7. Okay, 827 ohms for my RL1 loop. Okay, so next thing I'm going to do, I'm going to do the next piece in this. Well, my next piece is going to be right here. It's a 560 ohm resistor in series. So my loop for 1 is 703, and I'm just going to truncate this to 0.45 ohms. My R at number 3 right here is 560. Then I'm going to do this next loop. Well, this next loop is much larger, so I'm going to have to add these together first. So I've got what will be my R4, which is a 940 ohm, and my R5, which is a 2.6K ohm, which is 2600 ohms. So those two together are going to be equal to 3540, if I did the math right. And that means my R6 and R7, which is the next two lines, are right here. There's a 12K, 1.2K, and a 1.1K. So that's 1200 and 1100. And those together, that means, let's go 0, 0, 3 to 2300 ohms. And then it's my R8 and R9, okay, are these last two here. It's a 2.3K and a 1.2K. So that's 2300 and 1200. Bring those together. Well, I get 0, 0, 2 and 3 is 5, 1 and 2 is 3. So that's what I've got so far. So my resistance for loop 2 is, so I've got my resistance for loop 2 is going to be equal to, well, 3540 to the -1 plus 2300 to the -1 plus 3500 to the -1, and then I'll invert that back out. Again, I'll punch that into my calculator just exactly how I wrote it down. 3540 to the -1 plus 2300 to the -1 plus 3500 to the -1. And I'll bring that back to a whole number. I should get 997. Yep. So my resistance at loop 2 is 997.026. And then it's 1 and then 2 zeros. 1, and we'll just stop right there. So my resistance at loop 2 is 997.0261 ohms. Now, from here, if I look at my stuff, I've got a 47 ohm, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9. This is number 10. So my resistor 10 is in series, and it is a 470 ohm. So now I've got to solve this last loop here. Well, my resistor number 11 right there is a 55.4K, then a 6.9K, and then I've got to add this for 13 and 14, okay? So I'm going to go down here and say my resistor 11 is equal to 5,400. My resistor at 12 is 6,900. Okay, and my resistor loop, actually, my resistor 13 and my resistor 14 will be added together, but they are, what are they? I got too much paper in the way. 4.7K, so 4,700 plus 1,000. Bring those together, that's going to be a 5,700 ohm resistor. So now to get this loop right here, which is basically from 11 to 14, I'm going to have my resistor in loop 3 is going to be equal to parenthesis 5,400 to the negative 1 plus 6,900 to the negative 1 plus 5,700 to the negative 1, and then bring that back out to a whole number. So my resistor in loop 3 is going to be what? Let's plug that in, just like we parenthesis 5,400 to the negative 1 plus 6,900 to the negative 1 plus 5,700 to the negative 1, close parenthesis, convert it back to a whole number. I get 1978.038558. Okay, so I'm just going to truncate that a little bit over here. Call it resistor loop 3, and that's going to be 1978 point, we'll go 4 decimal places, 0386. Okay, we just round curled up. So that'll give me there. So get to that point. So that's up to resistor number 14. So resistor number 15 is in series, and so is resistor number 16. They're right here. 68 and 1K. 680 and 1,000. Okay. Now when I add all this up, it's going to be my resistance total. Okay. So I punch all those numbers in. So if I go 703.45 plus, whoops, delete that 560, plus 997.0261 plus 470 plus 1978.0386 plus 680 plus 1,000. I get 6388.5147. Okay, so that's going to be my total resistance. Now, once I have my total resistance, I can get my current total, my IT, by taking the ET, my energy total, and dividing it by my RT. Well, in this case, my IT is equal to 12 divided by 6388.5147. So if I take 12 on my calculator and divide it by the answer I just had, I get 0.00878. So my IT intensity total 0.00187837. Okay, we're just going to truncate that out. It's actually 1.88 milliamps when we round it down. So I can start plugging this back into my whole circuit now. Okay, we're going to pause for a few minutes, and I'll do a couple other things real quick. Hi. Okay, so what we did while we paused there was we went and solved all of the series circuits in this, all the series portions. So resistors number 3, 10, 15, and 16 are all in series. So at that point, all I need to do is know what the total current applied to the circuit is. In this case, it's 1.88 milliamps, and I multiply it in each case by the resistor and that gives me the voltage consumed by that resistor. Well, in this case, 3 absorbs 1.05 volts. Resistor number 10 absorbs 882.34 millivolts. Resistor number 15 absorbs 1.28 millivolts or 1.28 volts, and resistor number 16 absorbs 1.88 volts DC. Now from here we're going to do the same basic process, but we're going to do it with the parallels. We're going to start with this one right here, and I'm going to work on it. What's going to happen is this. I can figure out, because I know what these two are worth combined, they're worth 780 ohms. No, 703 ohms, roughly. I'll take that 703, multiply it by the current, and that'll tell me the voltage drop across both those two. If I remember right, I believe it's 1.3 volts, but I'll double check that. Then I can take that 1.3 volts and divide it by this number here, and then this number here, 1.3 volts, 1.32 volts as well. And that'll tell me how much the current is going through this leg and how much is going through this leg. Now, because of Kirchhoff's law, what's happening is the current is flowing out of our voltage source. It's hitting this junction right here, and it's going to split and go through each leg. But it's only the 1.88 milliamps total, so it's being split unevenly because these are uneven resistors. If they were the same exact resistor on each side, it would be an even split, but because it's not going to be. Now, I'm going to do that, and we'll come back and show you what we got in just a moment. Okay, sorry, pause there for a minute, did some writing. So I want to make sure we emphasize, this is multiply, okay? Because we're looking, we got a resistance value and we have a current. To get our energy, we need to multiply them together. We get 1.32 volts here and here because it's even. The way, okay, voltage is always constant in a parallel circuit, so both sides get the same amount of voltage drop. So now I'm just going to simply take this number, this 1.32, and actually I'm going to use the whole number up there on my calculator, but I'm going to then divide it by this 1200 here, and it's going to give me my I at 1. I'm going to do the same thing down here. I'm going to take this 1.32 again with that whole number, and I'm going to divide it by the 1700. That's the resistive value here. Let's give me my I at 2. So let's punch those in. So I've got that 1.32, and I'm going to divide that by 12, not 1 to 1. All right. So right here, I get that's equal to 0.00110111666. So if I truncate that down, I get 0.00110, okay, which is 1.10 milliamps. Okay, now do the same thing we did before. I'm going to take that total voltage and I'm going to divide it by 1700. Divide that by 1700 and I get equals 0.00077258882. Well, if I truncate that down, I'm going 123, I get 777.26, and this is microamps this time. So I get 777.26 microamps. Now, if I add this number to this number, I'm going to get this, where is it? Right here. This 1.88 or 1.878 milliamps, which is right. So I will repeat that for each of these parallel loops, and it will give me what I need to get done. So I'm going to pause this and go back and do that. Okay. Hi again. We're back. Let me explain what I've been doing, why I had this paused for a minute, why I got us cut up. So what I did is I went in and I figured out, because these are in series, so I just simply added them together so that I could then go back and show you what the total resistance for this loop right here is. Once I've got that, I can then go in and take this value and multiply it by, okay, the total current. It gives me the voltage drop in that loop because it is a loop. That means 1.87 volts is used up in this leg, and this leg of this loop. Now, once I've got that, I can then figure out, okay, a couple of things from that. Well, if I've got 1.87 volts being used up in this leg, well, its total resistance, when I add that 940 and that 2600 together, comes out to 3540. So if I take that 1.8727 volts and divide it by that 3540, okay, I'm going to get right here the total current in this leg. That will allow me to figure out how much of that 1.87 volts is used up in this resistor and how much of it is used up in this resistor. Because at this point, I now know how much current travels through this leg. I can repeat the process, take that 1.8727 volts, divide it by the 2300, that is those two added together, and I'm going to come up with 0.00081425425, or 814.25 microamps going through this leg. I can then take that current and multiply it by this value, and then multiply that current by this value, and it'll tell me how much of that 1.87 is being used up in this resistor and how much is being used up in this resistor. I can repeat that process a third time in this leg, as is shown right here, to figure out what's going on up there. So all I need to do at this point is take my numbers right here, okay, and start doing some simple multiplication. So if I take the 0.00052903525 and multiply it by 940, which is this current multiplied by resistor number 4, which is this one right here, and hit my enter button, I'm going to get, well, I'll just write it right up here. I'm going to get come on, pen, work, 0.497293135, or 497.29 milliamps in that one. It's a lot of it. Okay. Well, let's do the next one. So I'm just going to simply divide that 940 back out on my calculator. That way I've got the number back in. And now I'm going to multiply that number by that 2600. So that is 1.37549.165. Now, if I add these two numbers together, That's going to bring me to basically 1.87 volts between them. That's I'll do this for all of these. And that's what I'll do when I get down here to this circuit down here, or this portion of the circuit down here, and I'm completely solved. That's all it really takes. It does take time, and you kind of have to approach portions of it what some people consider backward, because honestly, you have to take what you know and find what you don't know. Okay, so that's it. I'm going to cut off right there so I don't solve the whole thing for class. So have fun.